This is a presentation about what we've learnt about bridges in this module. I'm John White and I'll be talking about the Pratt Truss and the Tamar Bridge field trip. In this presentation we'll give an insight to the Pratt Truss, our group field trip, the design process, build and test of a model bridge. In 1844, Thomas and Caleb Pratt patented a truss design which works using diagonals in tension and verticals in compression. This method allows dispersion of force throughout the entire frame, enabling the structure to carry weight greater than its own. The lightweight frame puts this at a logistical advantage when comparing it to an arch bridge, which is a common design used since Roman times in 84 BC. During this module, the group took part in a field trip where we learned about the construction and maintenance of both the Royal Albert Bridge and the Tamar bridges. Learning that the cables running either side of the bridge frame had been reinforced, giving the bridge added strength, led us to implement this concept on our design and add extra material to the outer frame of our model.
Hi, I'm Will and I'll be talking about our designs. Starting our bridge's design, we decided to make a Warren Truss bridge. The simple design would be easy for us to build and easy for us to model the forces acting upon it, meaning there would be little room for gross error in our building and predicting of the forces. We'd been taught about trusses in our lectures, and we knew this would be a good starting point. The design of a truss bridge spreads the force among the trusses until it reaches the bracing platform. However, we found from Atkinson 2008 that this results in the weakest point being in the centre of the base. We calculated that this design would take a predicted 13.9 kilograms before breaking in the centre. To improve upon this, we decided to try and make a bridge that uses compression in the outer members, so we designed a bridge that combined the truss and an archway. The compression in the outer members would remove some tension from the central decking and result in the forces being more evenly spread. Our new design had a higher predicted load of 33.3 kilograms, however the height of our designs mean we will likely make errors, and so we reduced that to our maximum weight of 25 kilograms. Boone 2016 showed us that a taller bridge would hold more weight. So, we finally chose a much taller bridge design with trusses going throughout. The trusses would reduce the load on each internal member, and the added height would put more compression into the archway.
I'm Ellis Flaherty. Our bridge weighed 175 grams and held a weight of 15 kilograms. This gives us a weight to load ratio of roughly 1 to 85. The bridge was quite heavy compared to other bridges, as our design required us to use all of our sticks. Our bridge ended up collapsing due to a lack in horizontal bracing. You can see in this picture where our bridge started to fail. If we was to change our bridge, we would try and add more bracing. We wasted a lot of sticks on the platform and in our vertical bracing. We could remove some of these and put them as horizontal bracing. The aim of our group work was to construct and build a freestanding bridge out of lollipop sticks and glue. Our bridge met the building criteria, but compared to other bridges, our weight to load ratio was below average. Our bridge ended up failing at 15 kilograms due to a lack in horizontal bracing. Compared to groups that did a Warren Truss design, this wasn't that good as they held about 30 to 35 kgs with a lighter bridge. Overall, our bridge didn't perform as well as others. This was probably due to overcomplicating our design, as this not only made it hard to build but also hard to predict. If we were to do this again, we would stick with a simpler Warren Truss design, as this design seemed to have the best weight to load ratio in testing.